Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So for part number 4, we will discuss about the efficiencies of a turbo machine. So for the first part, we will discuss about the efficiency of a turbine. Okay, about the turbine efficiency. So first we look at the cross-section drawing of the gas turbine engine. So we have three main components for gas turbine engine. So we have a compressor, a combustion chamber, and also a turbine. So in terms of mechanism, we will discuss the mechanism of gas turbine engine in part 1 for this chapter. Okay, next. So now we want to concentrate more on the turbine. So if you draw simplified schematic diagram, we will get the simplified schematic diagram as shown in the second figure. Okay, so for the turbine, the inlet condition of the turbine is number 3, and the outlet condition of the turbine is condition number 4 or state number 4. So for the turbine will produce the value out during the expansion process. So the process that involved for turbine is an expansion process. Okay, so in order to describe a process that we have learned in thermodynamic 2, so we need to draw TS diagram. So this TS diagram actually the TS diagram for Brayton cycle. So we have the process for the compressor from state number 1 to state number 2, and also the expansion process in the turbine from state number 3 to state number 4. So there are two processes for each component. First, for the ideal case, represented by isentropic process. For the turbine, the process starts with state number 3 to state number 4S. So S represent the isentropic process, the ideal process. For the actual process, represented by the process start from state number 3 to state number 4A. Okay. So this is the process for expansion process in a turbine, for actual and also for ideal case. However, because we already discussed about the stagnation point, where for turbo machinery we need to include the stagnation point and also the stagnation state. For the HS diagram, we need to include the pressure for stagnation pressure and also static pressure at the inlet of the turbine and also outlet of the turbine. So previously in thermodynamic 1, we just consider for the turbine we just consider static pressure, which is P3, the pressure at the inlet, P4 at the outlet. So now we have two type of pressure at the inlet of the turbine: stagnation pressure at the inlet, P03, static pressure at the inlet, P3. And we also have two different pressure at the outlet of the turbine: stagnation pressure at the outlet, P04, static pressure at the outlet, P4 for the turbine. Okay, so the state 03 and 04 represent the state for stagnation state. However, state 3, state 4 represents static state, and state 04S and 4S represent the isentropic state, which is 04S refer to stagnation isentropic state, and 4S static state, isentropic for isentropic process. And the term for the parameter for C3, C4 and C4 is the value of fluid velocity, C3 at the inlet, C4 at the outlet, which means the velocity of the fluid throughout the process of the expansion. And the term half C square represent the kinetic energy they obtained by the fluid during the process. Okay, so we need to know this diagram in order to to derive and also to understand the equation for turbine efficiency. And this line, the vertical line, represent the ideal process, and the decline line represent the actual process for the expansion in the turbine. So in terms of stagnation enthalpy formula, at the inlet of the turbine we will get the formula where stagnation enthalpy at the inlet of the turbine equal to H03 equal to static enthalpy at the inlet H3 plus kinetic energy of the fluid at the inlet of the turbine, half C3 square. And the stagnation enthalpy at the outlet equal to H04 equal to H4 static pressure at the outlet, static enthalpy at the outlet plus the term of kinetic energy of fluid at the outlet of the turbine. So these are the the stagnation enthalpy formula for the expansion process in the turbine. Okay, now we look at the general equation for turbine efficiency. So there are three equations under the turbine efficiency. So first we look at the figures. So this figure shows the quarter cut of gas turbine engine diagram, where it consists of single stage compressor and double stage or two stages turbine, as shown in the figures. Okay, so our concentration is on the turbine. Okay, so now if we draw simplified the diagram, so we'll get this diagram where we just focus on the turbine. Okay. Okay, so now the first general efficiency equation for the turbine we call overall efficiency, represented by mu naught or mu 0. So the efficiency of turbine in terms of meaning, the meaning of the overall efficiency is the efficiency of the turbine to convert the available energy in the flowing fluid into useful mechanical work delivered at the coupling of the output shaft. Which means, okay, the energy from combustion that transfer to the fluid, that represented by the pink arrow. So this energy will use to rotate the turbine. So in actual condition, due to the energy transfer, heat losses to surrounding, pressure difference, pressure drop, friction and so on, there will be energy losses throughout the expansion process in the turbine. Okay. So after turbine, in terms of work output that produced by the turbine, so you will get W out. So the energy that released from turbine, which is represented by the green arrow. Okay. Okay, so further, due to the mechanical rotation of the shaft and also the coupling, there will be more energy losses throughout the process. So the energy that received by the electric generator that attached to the turbine will be lower than the energy that produced by the turbine. So the useful work that represented by the blue color arrow represent the energy that received by the generator after we consider the energy losses throughout the process. Okay, so now the formula for overall efficiency, mu naught equal to mechanical power available at the coupling of output shaft divided by maximum power difference possible for the fluid. So maximum power difference possible for the fluid refer to the energy that received by the fluid that used to rotate the turbine blade or turbine rotor. Okay, represented by the pink color arrow. So energy that obtained from the combustion process. And the mechanical power available at the coupling of the output shaft represented by the energy of useful work that represented by the blue color arrow. Okay. Okay, the second general efficiency for the turbine we call isentropic efficiency mu T, where the formula for mu T, isentropic efficiency, equal to mechanical power supplied to the rotor divided by maximum power difference possible for the fluid, where maximum power supplied to the rotor, which is represented by blue color arrow, divided by maximum power difference possible for the fluid, represented by pink color arrow. Okay, so the combination of this general efficiency of overall efficiency and also isentropic efficiency will get new terms for turbine efficiency that we call mechanical efficiency, represented by mu m symbol, where mechanical efficiency mu m equal to overall efficiency mu naught divided by isentropic efficiency of the turbine mu T. So these are general equation for turbine efficiency. So now you need to know what the difference between these three equations, and also you need to know the meaning of the value for different type of efficiency for the turbine. So okay, there are another I call expression to determine the turbine efficiency. So this expression consider more on the function of the turbine, so that by using the expression we will get more accurate turbine efficiency based on its function. Okay, so now shows the HS diagram, where this diagram shows the process involved with expansion process in the turbine, involved with idle for the idle process and also the actual process. So we need to refer to this HS diagram because in this expression that we will discuss later on will involve the parameter and also the variable that state in this HS diagram. So the first expression of efficiency that can be used is total to total efficiency, mu TT. Okay, so the term total to total actually represented by the blue color line, which is represent the total to total process, and the process start with the total or stagnation state of 03 to total or stagnation state of 04s. And this expression of efficiency normally used for turbine where the exit kinetic energy is usefully employed, such as aircraft gas turbine and also multi-stages turbine for the gas power plant. This is the example of the jet gas turbine engine, where this kind of turbo machine will use total to total efficiency to determine its performance. So from this gas turbine engine, the energy that produced by the turbine will fully employed, where the energy will use in the diffuser to produce thrust force. So the equation for mu TT equal to, so the efficiency for total to total efficiency formula equal to mu TT equal to delta WT divided by delta WT maximum. So delta WT represent the term for enthalpy difference for the actual process. However, delta WT maximum represent enthalpy difference for the ideal process of the expansion. And this equation also equal to H03 minus H04 divided by H03 minus H04S. So H03 represent the enthalpy at the inlet of the stagnation state, H04 stagnation enthalpy at the outlet of the turbine, and H04S stand for the stagnation enthalpy at the outlet for isentropic process. If we neglect the kinetic energy difference, or we neglect the kinetic energy terms for the enthalpy, if we refer to the HS diagram, this term refer to the kinetic energy of the fluid at the inlet and also at the outlet of the turbine, half C3 square and also half C4 square. So if we refer to the stagnation enthalpy formula H0, H0 equal to H plus half C squared, where in the equation we will have the kinetic energy equation for the fluid. So if we neglect the kinetic energy, the term for the kinetic energy can be neglected. So now we will have the value of stagnation enthalpy will be equal to the value of static enthalpy. So we can simplify the total to total efficiency equation mu Tt to mu Tt equal to H3 minus H4 divided by H3 minus H4S. So instead of we use stagnation enthalpy value, so now we can use the static enthalpy value to determine the total to total efficiency for the turbine. Okay, so the second expression for the turbine is total to static efficiency mu Ts, where we can see from the HS diagram. So the process of total to static refer to the process where the expansion process start from 0, 3 for the stagnation point or the total point to the static point, which is represented by state 4S, and this process for the total to static ideal process. Okay, so normally the expression of the efficiency will use for the turbine where the exit kinetic energy is not usefully employed and entirely wasted, such as the rocket auxiliary turbine without diffuser, where the energy that produced by the turbine will release to surrounding, not fully utilized. Okay, this is the example of the auxiliary turbine photo or figures. So in terms of equation, so mu Ts equal to H03 minus H04 divided by H03 minus H04S plus half C4S square. So if we refer to the HS diagram, this equation also same as mu Ts equal to H03 minus H04 divided by H03 minus H4S. So we can see clearly, we can see from the HS diagram. If we ignore the kinetic energy terms, so we can, instead of we use stagnation enthalpy value, we can use static enthalpy value, where mu Ts equal to H3 minus H4 divided by H3 minus H4S plus half C3 square. So these two expressions of efficiency depend on the function of the turbomachine. So the usage of these efficiency equations depend on the function of the turbomachine, whether the energy that produced by the turbine is fully utilized or not fully utilized. Okay, now let me look at the difference between auxiliary turbine or auxiliary power unit APU with the typical gas turbine engine or jet engine. So auxiliary power units APUs are gas turbine engines used primarily during aircraft ground operation to provide electricity, compressed air, shaft power for main engine start, air conditioning, electric power and other aircraft system, APUs can also provide backup electricity power during in-flight operation. So in terms of main component between auxiliary power unit and also the typical gas turbine engine, so we can see that both turbo machine will have the same main components such as compressor, combustion chamber, and also turbine. So the main difference actually is the function of the turbo machine. Okay, as if we look at the schematic diagram of the aeroplane, you can see that in the red region shows the location of the jet engine or jet gas turbine engine, and this photo shows the detailed component in the gas turbine engine or jet engine, and the yellow arrow shows the direction of the fluid throughout the engine. And the second figures also shows the cross-section drawing of different type of gas turbine engine, which both figures shows the same main component of engine. And at the back of the engine, we can see that there is a device that we call a nozzle, and this nozzle, the function of the nozzle actually to produce thrust force in order to make sure that the aeroplane move forward and also fly into the air. So we call it freezer. This component we call this component we call nozzle, a nozzle. And if we look at the cross section of the nozzle, the diameter of the nozzle reduced throughout the process. Okay, so this kind of features will produce thrust force for the jet engine. Okay, so because the energy that released by the turbine will use to produce the thrust force, so the energy that produced from the turbine is fully utilized by the engine, where the engine will produce thrust force. So the equation that's suitable to determine the performance of this kind of turbo machine is total to total efficiency, mu TT, where the exit kinetic energy is usefully employed. However, if you refer to the blue color region where the APU, auxiliary power unit, is located, so this APU in terms of features similar like the jet engine in terms of inner component. Okay, these are the actual photo for APU. So if we get the drawing for the cross-section drawing of the APU, you can see that at the end of the APU, you can see that similar shape like the nozzle. However, in terms of cross-section inside the component, we can see that the diameter is constant, no diameter change, no volume change. So there will be no thrust force produced for the APU. So that's why the suitable equation in terms of efficiency for the APU is total to static efficiency, where the exit kinetic energy is not usefully employed and entirely wasted. Okay, to test your understanding, please answer the question below. What is the difference between total efficiency and also total to static efficiency? The second question, what is the unit for specific work done based on the Euler equation and the enthalpy difference equation? So you have to answer the questions by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic, and also the clue also is given in the link. Okay, that's all for part number 4.